The electrode potential does not depend upon the size of the electrode. It means the electrode potential does not change no matter how big or small the electrode is. The question comes why? So we can explain it by using one example, that is dissolution of salt in water. By the end, we will connect this to chemical kinetics and chemical equilibrium and why increasing the electrode size affects cell life but not the potential. So let's think about the dissolution of salt in water. When salt dissolves, it releases ions into the solution. The speed of dissolution depends upon how much salt is exposed to water. It means its surface area. But the concentration of the ions at equilibrium does not depend upon the size of the salt. It is a fixed property determined by the system's nature. So electrode potential works the same way. It is governed by the local environment around the electrode, that is, the concentration of the ions near its surface. This makes it an intensive property, meaning it doesn't change with the size of the electrode. So we can have two cases, a small copper nail and a large copper rod. Both are dipped in an identical solutions. It means the concentration of the solutions in both the cases are same. The nail has a small surface area, so fewer ions interact with it at any moment. The rod, with its larger surface area, allows more ions to react simultaneously. However, the local ion concentration at the electrode surface remains the same in both cases. This means the reaction quotient in the Nernst equation, which determines potential, stays constant. So it results that the electrode potential remains unaffected by the size of the electrode. So while potential doesn't change, increasing the size of the electrode affects the rate of reaction or chemical kinetics. A large electrode offers more sites for the reaction, allowing ions to transfer electrons faster. This increases the current but does not affect the potential. So now consider the equilibrium. Larger electrodes facilitate faster reactions, meaning the cell reaches the equilibrium faster. This also means cell's useful life shortens because of the reactants are consumed more quickly. In simpler terms, increasing the electrode size makes the cell work harder and depletes its energy faster, even though the potential stays the same. So let's go back to our salt example. A bigger chunk of salt dissolves faster because it has more surface area exposed to water. But the maximum concentration of the ions in the solution, the saturation point, remains the same, no matter size of the salt piece. Similarly, a large electrode speeds up the reaction but does not change the potential, just like a bigger chunk of salt doesn't change the saturation concentration. Electrode potential depends only on the local ion concentration near the electrode surface, not the total number of ions in the solution or the electrode's size. This local environment controls the equilibrium between the oxidation and reduction reactions at the interface, ensuring the potential remains the constant. So in conclusion, electrode potential is an intensive property because it depends solely on the local ion concentration. Increasing the electrode size speeds up the reaction and shortens the cell life due to the faster kinetics but does not affect the potential.